Now let's talk about data warehouses. So data warehouse represents a specialized type of database designed specifically for analytical processing rather than day-to-day transaction processing. As a central repo for data, a data warehouse is optimized for fast query and analysis rather than frequent updates. The key distinction here is purpose. While operational databases are designed to handle lots of individual transactions quickly, like processing loan applications or recording payments, data warehouses are designed to answer complex analytical questions across large amounts of historical data. Data warehouses typically contain historical data from multiple sources within an organization. For risk management, this might include years of transaction data, customer information, market data, economic indicators, and external credit bureau information, all integrated into single, consistent format. The central repo concept is very important here. Instead of analysts having to access multiple systems to get the data they need, the data warehouse brings all relevant information together in a standardized format. This integration is essential for comprehensive risk analysis and AI model development. Data warehouses are optimized for analytical queries that might examine millions of records to identify trends, calculate portfolio risks, or train machine learning models. These systems use different storage and indexing strategies compared to operational databases, prioritizing query performance over transaction speed. The structure of data warehouses often differs from operational databases too. While operational databases are normalized to eliminate redundancy, data warehouses are often denormalized, meaning some data redundancy is accepted in exchange for faster query performance. For AI applications in risk management, data warehouses provide the comprehensive historical datasets needed to train predictive models and the analytical power needed to validate and monitor those models over time. Graph databases represents a specialized approach to data storage that focuses on relationships between entities. In a graph database, data is stored in terms of entities and the relationships between those entities, making it particularly powerful for certain types of analysis. The structure consists of nodes, representing entities like customers, accounts, or transactions, and edges, representing relationships like owns, transfers to, or is similar to. This approach is fundamentally different from the table-based structure of relational databases. Graph databases are particularly powerful for risk management applications because many risk scenarios involve understanding networks of relationships. For fraud detection, you might want to identify rings of customers who are all connected through shared phone numbers, addresses, or transaction patterns. Traditional relationship databases can struggle with these types of network queries, but graph databases excel at them. OLTP databases, which stand for Online Transaction Processing Databases, are reported here because they represent one category of graph databases. An OLTP database is designed to be speedy and analytic, handling large numbers of transactions performed by multiple users simultaneously. Graph databases can process complex relationship queries much faster than traditional relational databases. For example, finding all customers within 3 degrees of separation from a known fraudulent account, a query that might require multiple complex joins in a relational database becomes a straightforward graph traversal operation. In risk management, graph databases are increasingly used for anti-money laundering investigations. For fraud detection, customer network analysis, and understanding systematic risks that propagate through interconnected financial relationships. The ability to visualize and analyze these relationship networks provides insights that are difficult or impossible to achieve with traditional tabular data analysis. Object-oriented databases represent a different approach to data storage, where information is represented in the form of objects similar to object-oriented programming languages like Java or C++. In object-oriented databases, data and the methods that operate on that data are encapsulated together into objects. This is fundamentally different from relational databases where data and processing logics are separate. This approach can be particularly useful when dealing with complex data types that don't fit neatly into traditional tables and rows. For example, in risk management, you might have complex financial instruments like derivatives that have intricate structures, embedded calculations, and sophisticated behaviors. Representing these as objects can be more natural and efficient than trying to decompose them into a relational table. Object-oriented databases can also handle multimedia data more effectively. If your risk management system needs to store and analyze images, say check images for fraud detection, or videos like surveillance footage, or complex documents like loan agreements with embedded signatures and annotations, object-oriented databases can manage these complex data types more naturally. However, object-oriented databases have not achieved widespread adoption that relational databases enjoy. They tend to be used in specialized applications where the object model provides significant advantages over the relational model. The integration with object-oriented programming languages can provide performance benefit and reduce the complexity of data access code, since the database objects can be manipulated directly in the programming language without translation layer. So, the fundamental concept behind object-oriented databases is that all entities should be treated as objects that encapsulate both data, which are attributes, and processes, which is behaviors or methods. This encapsulation means that an object not only stores information, but also contains the logic for manipulating that information. For example, a loan object might contain data like principal amount, interest rates, and payment history, but it might also contain methods for calculating current balance, determining if payments are late, or assessing default risk. Object-oriented database management systems are mainly used to support multimedia applications or systems that involve complex data structures. In risk management, this might include systems that need to handle complex financial instruments, multimedia fraud evidence, or sophisticated risk models with embedded business logic. The advantage of this approach is that it can reduce the mismatch between the programming language and the database. Instead of translating between objects in your program and rows in database tables, you can work with objects throughout your entire system. However, object databases play a minor role in the market today. Most organizations continue to use relational databases for their primary data storage needs, sometimes combined with object-oriented programming layers that handle the translation between objects and relational data. The concepts from object-oriented databases have influenced modern development, like NoSQL, document databases, and object relational map frameworks that provide object-oriented interfaces to relational databases.